this. Okay. So it directly interacts with this particular skin. Where do I have to? Here or here? Okay. Got it. All right. Thank you for the very nice introduction and for the invitation and arranging this talk, this seminar in a very short notice. And also thank to those of you who have decided to show up despite this very short notice. That's very highly appreciated. So this talk is going to be an overview of two different subtopics that bridges physics and machine learning together. The first one bridges fundamental physics with theory of deep learning through a mathematical correspondence. And the second one is an application of Wilsonian RG, that is application of fundamental physics for theory of deep learning, not so much of a correspondence, but rather just developing a framework for better understanding of theory of deep learning. So this has the implication where we can understand machine learning and AI better and leverage that understanding for better simulations of quantum field theories, and maybe going beyond QFT. Right now we are working towards SUSY field theories. Now here it is the reverse direction. You take advantage of machineries you already have in fundamental physics and equip this whole community that's just exploding with this excitement with actual mathematical understanding and some new results that they have not obtained before. So this is based on a number of papers listed over here, as well as this is linked with many other related works that has emerged over the last 4 to 5 years. Now, without further ado, let me just tell you more about an overall reason to care about topics which look like this at the intersection of theoretical physics and machine learning. Well, even if you don't care about deep learning deeply, there is still a good reason to care about it lightly, as in, just for the sake of applications of these machine learning and AI technologies, in order to hopefully find some new results in the domains of strings, QFT, quantum many-body physics, quantum computing, and last but not the least, very importantly, this ML-driven discovery, automated theory exploration, which someday would be very important as we'll keep seeing more and more results from future runs of the LHC and other colliders. And when we would try to explore the space of possible effectives as much as EFTs, effective field theories, as much as we can, in those points it would be very important to automatize that search of parameters or symmetries or anomalies rather than just leaving it to this human computational powers. Now, many of you, I believe, would be familiar with these set of works over here. This is, in case you are not familiar, this is one of the seminal papers that built up something known as normalizing flows, which is a very effective way to apply machine learning for field theory and lattice. But then there are problems, well, with supersymmetric field theories, this actually breaks down. There is a sign flip problem that happens because of the fermionic nature of the fields. So there are challenges here. As for here, string theory landscape, those of you who went to the strings in Abu Dhabi this time, I'm sure you have heard about works from a number of people. This Fabian and this Jim Halverson, who was my PhD advisor, they have worked intensively on this. There are also other people, Vishnu Jejala, Gary Xu, who have tackled different problems, Yang Hui He. Now there has emerged a second and third subdirections which are equally exciting. This one is actually very promising. The scattering amplitudes in super Yang-Mills theories are being right now explored and predicted and computed using transformers, which are the backbones of large language models like ChatGPT. Lance Dixon and Tianji Kai, Kyle Cranmer, a few others, they are running this research program. And then there is Koji Hashimoto and others in Japan group who are using machine learning for ADS safety correspondence and the reverse, ADS safety, various concepts from here for a better understanding of deep learning. So that is all good. So that just tells us one thing: machine learning can be effective as a toolbox for physics. But is there anything that we should still pay attention to, and before we just take these toolboxes, download them from GitHub, and just apply them for physics? The short answer is yes. The long answer is long, and I will not go into that. Let's focus on the short answer. Yes, there is something to actually check before you apply these methods for the problems that you're interested in. And you have to make sure that these packages are effective. These packages are trustworthy. Trustworthy in the sense they should produce outputs that adhere to some standards that define what scientifically rigorous answers should be. Generically, take any diffusion model out there, Stable Diffusion, Midjourney, or the O3 model of ChatGPT. Sometimes they give you answers which will make you believe AI is garbage. And those are not the kind of answers you want for whatever problem you are looking into, because it might produce garbage instead of learning something useful from the physics problem. But the garbage might look very significantly close to the real answer, maybe differing by 1 sigma, 2 sigma. You don't want to go into that scenario. So then what can we do such that what can we do such that we can at least ensure that the packages we download and the methods we use for fundamental physics, that those are reliable? Well, there are certain properties of the AI packages you can pay some attention to. And in fact, in order to determine these properties, you have to actually use your knowledge of fundamental physics. You can't just take any package and just look up some other ML GitHub page to find what those properties are. This is where your expertise has to enter and determine that these properties for your problem is being maintained by the package you're using. So in a nutshell, there are 3 keywords that I've thrown out there, and I'll define them in the next page. Now, there are also the very cool words that you will see here and there on newspapers, but these are not that relevant for physical sciences. These are more for AI for healthcare, AI for law, etc. These are what you need for AI for mathematical sciences, more importantly. So let me go ahead and define what those are. The first one is precision, and precision is in the same sense we define precision in physics. So if there is some data that ML model is processing, there is this flow, this algorithmic processing of the data through the model. If, as a physicist, you know that there is some hierarchy among the data attributes, and the final result is depending significantly on a class of data attributes over the others, you should expect that the ML model, in the process of creating the outputs, would somehow learn this intricate relation between the data attributes. So much so that if you are supposed to, suppose you coarse-grain some of the data attributes out in a way that the main result should not change much. So the machine learning output should know that, well, whatever has been removed was not very important to start with, and its answers should accordingly auto-tune, and it should not just spuriously change with no relation to the actual correlations between data structures. The second one is interpretability. This depends on an ability to actually process the data as it should. What do I mean by that? Just think of a simple example, a function, sine of x. And suppose you are using machine learning toolbox to learn this function, sine of x. Now, within the range from minus pi by 2 to pi by 2, it might give you correct sinusoidal graph, but it might just give you something totally different from the range 3 pi over 2 to 5 pi over 2. Now, is that what you want? No. So an interpretable AI means that you should be able to peek into the model, and you should be able to tell that, well, I passed x, and it took x, and then composed sine with x. And how do I know it's sine? Well, you can see in this layer, if you Taylor expand whatever function it is there, then the first few terms match with the Taylor expansion of sine x. So you should be able to interpret out what this ML model is doing. It doesn't have to be completely a black box. Because if you're not able to read anything into the box, there is no way you can guarantee that the results it is giving you is actually meaningful, or whether this is just a glorious data fitting tool that's just going to break down at the next data set. And thirdly, there is robustness, which depends on an ability to correctly, sensibly autofill for missing information. What does that mean? Take an example, take ChatGPT and ask it, can you prove 2 plus 3 equals 5? It'll give you some proof that makes no sense. Why? Because if you actually ask it to give you the proof and then say that, well, that was incorrect, 2 plus 3 equals 7, then it'll give you the same proof, or similar kind of proof, saying, oh yeah, I was wrong, 2 plus 3 equals 7, and give you some very nice lines to support that claim. Now, that is not a robust model, that's hallucination, and you want something that actually can autofill the line of thinking, the reasoning behind why 2 plus 3 equals 5. That's actually an artificial intelligence. Anything else is just more or less statistical regression toolboxes of many various complexities. So with these 3 key definitions, then let me emphasize why, as theoretical physicists, we cannot just take our hands off from these AI and machine learning toolboxes. Why do we have to at some point peek into these, make sure that they are at least embedded with some physics information? You know, physics informed neural networks, for those of you who are familiar with this keyword. What this means is that you have to take neural network architectures, which are backbones of these ML and AI models, equip them with some constraints that ensure that physical rules and physical properties are respected in some regard as this machine is trying to pick up data features, data attributes, and data properties. And in the process, it'll become a more reliable toolbox for physics. It'll become something that can adhere to some scientific benchmarks. And there is another key point to keep in mind. So there are a lot of modern state-of-the-art AI results out there. These are empirical success. The empirical success is not always backed up with good theory supporting why it is working or when it is going to break down. And this is one of the biggest fallacies that those of anyone who is working at the intersection of machine learning for science is actually concerned with. We don't have any idea when these models are going to break down. And if we don't know when these are going to break down, we cannot actually trust these models to produce the results for new generation discoveries in physics. But that's actually where we need these models. So someone has to do the job. Now, there is research to ensure these kind of things. The AI industry and some computer scientists, some people in statistics, machine learning intersection, they do put out results, and those are very hard to translate into the language of theoretical physics. Also, it's a nascent field. There are a lot of empirical results like Paolo curves. There are various scaling laws that have very little explanation. So somebody has to actually make sure that those scaling laws are not spurious result scaling laws. You have to make sure that those scaling laws actually correspond to the real outputs as it should be. But for that, you need some kind of theory. Only theory can tell you that some scaling relation between a model's parameters and the output's dimensions should look like this. Without proper theory, there is no way to guarantee that the empirical results you are seeing actually are sensible, or whether they are coming from some kind of hallucination and mistakes. And thirdly, the most important reason why you should care about this intersection of AI and physics is because as the data length scales change, by that I mean as the length scales of the problems from which you have sampled the data, test and train data, as that changes, the performance of these ML models can break down unpredictably. You can just train a model, you can take AlphaFold, but can you really trust it with the LHC data? The answer is nobody knows. Yeah, and you should not trust it to work unless you have some guarantees. So that is all good, but the point is, what can we do? How much have we done? So it is a nascent field. Very recently, since the last 2 to 3 years, 3 to 5 years, theoretical physicists have started caring more and more about equipping ML models with meaningful physics constraints, physics-based constraints. And to that end, I have done some work that explores how we can connect these 2 areas and how we can make sense out of machine learning and AI. And I will discuss 2 particular subtopics that explore this intersection. The first one is neural network field theory correspondence, and the second one is the Wilsonian RG for supervised learning performance. Now, the whole point is that both of these, if you pay some attention, you will see that these are more or less general frameworks, so you can extend them to other cases as well. And with coming years, people will have to do that more and more. So the first one, this has been a research program that started since 2020. And outside of the papers that my talk is based on, there has also been This same framework extended to the case of conformal field theories that came out from Jim Halvorson and others this summer. And there is currently work on minimal supersymmetric field theories that we hope to publish in a few more months. And we have made progress with free fermions as well. So first, why a new program altogether? So what is this program concerned about? This is about machine learning for quantum field theory. To that end, we develop a correspondence. And this correspondence was necessary because so far, when we started developing it, the standard machine learning for QFT, they were very successful up to numerical precisions, but there was no way to guarantee that the machine learning model through this workflow of processing the data was actually developing a sense of what quantum field theory is. So what we wanted was actual artificial intelligence about field theory developing through the process of this ML for QFT. There was no guarantee. And as most people believed, it was probably a very rigorous data matching, curve fitting. So we wanted to move away from that very rigorous curve fitting, and we instead wanted to equip these neural networks with better expressivity. What does expressivity mean? Expressivity means that these models should be able to intrinsically know what a quantum field is, in the sense that its degrees of freedom should be related in a way that actually its degrees of freedom should be related in a way so that the output has to look like a quantum field just through this correlation of its degrees of freedom. And in that sense, you are essentially constraining the architecture itself to resemble some physical theory. It cannot give you something ad hoc. So that's how it became more interpretable. So we wanted to do that, and we went back to the backbones of machine learning, neural network architectures, and embedded as much information as possible. So one key point here is that by no means we will claim that this is the best way to sample quantum field theory using machine learning. No, this is one of the ways, and in future we hope that there will be amazing ways as well, except that we don't have great methods right now, so we needed more methods, and this is towards one of those. So far this provides an alternate sampling method for fields and lattice, which this method is more precise, it makes less mistakes by definition. It is interpretable because we embed information, we know how the information gets embedded in the neural network, and we also know how the output is constructed, why it should look like a quantum field. We have a guarantee that it has to look like a field. And lastly, it has no scopes of hallucination. As a result, test loss is guaranteed to be 0. Now, test loss is also known as generalization error. So this is actually a mapping, a one-to-one correspondence between the space of all architectures and the space of statistical field theories. Now, in certain cases, the statistical field theories will allow analytic continuation to the Lorentzian background, and in those cases, this will map to quantum field theories. So a priori, it is not just useful for particle physics strings, but it is also used for condensed matter and those of any other domains that use statistical field theory. Now, also the key point is this is a correspondence that's a mathematical duality, not a physical duality, and this is true at initialization. Initialization means you have not talked about how many GPUs you are going to use for training. You are cutting down all compute resources. There is no back propagation, only forward pass, one single forward pass, and that's it, you are done. So initialization is where training algorithms do not appear. You only deal with this graph-like structure called neural network, and it is then going to give you a target statistical field theory that you had in mind. That's the power of this correspondence. Now, some step-by-step overview into how that happens. So the first one, the inputs correspond to space or space-time points, and the outputs correspond to field. Now, you could define the inputs to be Riemannian manifold, and then the output would be basically the fields for all points on the Riemannian manifold. Now, if the if the inputs are instead a series of numbers, you can treat those series of numbers, a set of numbers, as a lattice, which may be one-dimensional or two-dimensional. And the output is going to be field corresponding to some dual field theory, which is decided by some dual action. But the field is then evaluated on this set of inputs. And this works because, by definition, if you could create a statistical ensemble of any randomly initialized neural network architecture's outputs, that statistical distribution can be promoted to a Feynman path integral. And there it is a functional distribution, and you can actually, using architecture details, infer what the action looks like term by term as a series sum over free term and then hierarchical interaction terms. So that's why you are able to actually create a field theory out of neural networks. You define a field theory here, and the field theory defined by neural network is the NNFT. Now the origin of the interactions in the action is actually due to the violations of Central Limit Theorem. Now I don't know how much scope I will have to explain this one. Let me briefly put it this way. Neural networks outputs are actually the normalized sums over many non-polynomial functions that come out of many nodes in the very last layer. And as long as you have got the architecture defined using stochastic parameters, which are sampled from statistically uncorrelated and identical distributions, then these contributions from each of the nodes, they are statistically uncorrelated. And then this normalized sum becomes a sum over many statistically uncorrelated random valued function. And then you can do some mathematical manipulation to show that if n goes to infinity, this is a draw from a Gaussian functional distribution, as in the action has only a quadratic term. So then that is equivalent to a free field theory. Now if you could violate these constraints on the architecture given here, then you turn on non-Gaussianities in this functional distribution. So in that way you are controlling how you turn on interaction terms. And if you violate these terms pretty badly, you are going to get a very non-perturbative field theory. The point here is that when you are violating these constraints or protecting them in the architecture, you actually have very little. At that point you can be completely agnostic on the structure of the action. Without knowing the structure of the action, you can control the nature of perturbativeness, of whether they're highly non-Gaussian versus not, whether they become non-Lagrangian non-perturbative theories or not. Then this is just an overview of many related works and how this NNFT correspondence connects to the other programs out there. Now let me go on to the other important detail here. I just have mentioned that for any generic architecture, you can actually obtain a dual action as a series sum. So without too much detail, there are a set of Feynman rules that allow us to do this. This happens because in using statistical physics, there's a method called Edgeworth expansion. What that lets you do is, for any statistical distribution you have got out there, among which neural network output ensemble is one of them. So you can have any statistical distribution, and you can write down the probability density of it in terms of all the connected correlation functions. Then you can actually massage that equation to take this particular shape, where you get the expressions of a quadratic term that looks like a free term with a kinetic operator. You have other higher order terms that look like these polynomial interaction terms. So the point to remember is that the reason we have these polynomial interaction terms is because it's an infinite sum. So the idea here is that when you are going from an architecture to its dual action, you don't necessarily get a non-perturbative action as one single term. So then what you would get actually is an effective action. You would get this term plus many terms like these, and these actually have intrinsic scaling. Sorry, I'm not going to explain all of this because, you know, the details, but you can ask me afterwards if you're interested. One can prove a theorem that these have intrinsic scaling that depends on the number of nodes in the hidden layers of neural network architectures, so number of nodes in the graphs. And depending on those number of nodes, you have 1 over n. N is the number of nodes, 1 over n scaling associated with all of these. So then these have intrinsic scaling associated with each of the couplings, and you can always truncate this at some sensible order. So yeah, that's a very good insight. So the rotational invariance actually, so if it is global rotational invariance, that is built in as long as the parameter distributions have a global rotational invariance. because there the symmetries of the parameter distributions shows up directly here and here. Now, if you're talking about gauge invariance, we have not yet cracked that problem open.
You can, for instance, so the matter is the time and space.
Yeah, exactly.
Other question was that it seems like you are not allowing for a linear term, a tadpole term in the.
Yeah, that's right.
How are you ensuring that?
Okay, yeah, very good question. So right now we ensure that by making sure that the mean of the parameter distributions are 0. If mean is 0, then the linear term actually is going to vanish, because the linear term depends on a mean value of each of these parameters. Now, if you fully train a neural network, then the outputs are going to develop a mean value, non-zero mean value. And that's when these tadpole terms would naturally appear, because you cannot get rid of those anymore. Sorry?
When you use the central limit theorem
Yeah.
to take it towards the free field,
Yeah.
there the distributions that go there for the parameters.
Yeah.
You do not demand that the two distributions have 0.
No, we don't demand that, right.
At that level, you actually have that.
Yeah, right. This is just a simple demonstration of how the action looks like. So you could start with a convoluted probability distribution of the parameters, and as a result, you can have a non-zero mean value to start with. And this action over here then indeed is going to have a tadpole term. We wanted to keep this as simple as possible, but you can indeed have a remaining term here. Now, yeah. That's a very good question, and yeah, let me address this question. So we actually try to have derivative interactions. We found that that is actually kind of hard, unless maybe you use a filter, like this convolutional neural networks use a filter. Why? Because in general, if I go back a few slides, maybe go back here. So these actually don't necessarily take into the difference of the magnitude of different input points. So what is a derivative? You need to, for a derivative term, you need to have something that's a difference between phi of x and phi of y, if you think of it discretely, and then divide that by the difference between the inputs. That's like having a convolutional filter, right? Yeah, that, in case you are not aware, that's a convolutional filter. So in CNNs, people have that, and in many other networks, people have that. But not all architectures come equipped with that. So essentially, if you want to have some kind of a derivative term, then you have to design an architecture more convoluted than what I had presented, a simple one. So this is very generic, but indeed, derivative terms can appear. And let me just go a little down to see if I can present one. I think I have some examples with derivative terms. Let me see. Our papers certainly have an example with derivative terms. Okay, we do have one. So this is an example of an architecture where you have got a single hidden layer network. It has got cosine activation function, and these are the parameter distributions at initialization. And we actually computed the free term, the kinetic term and the leading order interaction term, which is a quartic. Sorry. And what we actually got here was we had double derivatives which appeared as part of the coupling, not necessarily derivatives of phi, but then you can expand this one out, and from this you will generate derivatives of phi. So you have to kind of massage these expressions to get the derivative terms that you are looking for. Right, so yeah. It's a double derivative on Euclidean space. Yeah, that's right. You could also make a local action with derivative terms if you play with the architecture. So right now I don't have the scope to demonstrate that one because we did not evaluate that one, but in principle you can also get something like that. Oh, it does. It totally does. So the reason we chose Gauss was because we realized if you can this is an inverse propagator. The inverse propagator has, this double derivative in the exponential, and that gave us intuition that so this guy over here, the quartic coupling, actually is related to the fourth cumulant, fourth connected correlation function of this function, functional distribution. So from this we could infer, at least if you look at the fourth order connected correlation function, the paths that you subtract out in the connected correlator, that is going to have terms that look like this. So then we wanted to also see whether the actual fourth correlation function of this network also had a derivative structure. It did, so we could write out this way. But if you think about this, if as long as a network has a propagator that is a two-point function of the output that has a derivative structure, all of the couplings which are related to these connected correlation functions and therefore will have contributions from the propagator, inverse propagator as well, they are going to have derivative terms show up.
And is the reason you choose different parameter distributions for the weights in the bias?
Yeah. That's a very good question. And yes, there is a reason. So we chose this because this gives us translation invariance. So I have not talked much about symmetries, but what this does is that this action is translation invariant. And we ensure this translation invariance by limiting the symmetry of these probability distributions to through here. So the bias being translationally invariant gives us special translation invariance of the theory. Yeah.
So here you seem to have different parameter distributions for different.
Mm-hmm.
If I have the same parameter distribution for all of them,
Mm-hmm.
then would I have a free theory? I thought the free theory is all the parameter distributions are the same for all of them.
That's a good question. The short answer is no, because we have considered finite width network. If n goes to infinity, this term is going to, yeah, then you will have a free theory.
But if now here n goes to infinity, I will still not have a free theory because my parameter distributions are.
Oh, okay, no. I think that has confused you. So each of the parameter, like W0 itself, it is statistically uncorrelated from the rest, and it is identical amongst itself. And this guy is not also statistically correlated, and it is identical. Each element, you can look into the dimension.
So the statement that all the weights for a single layer,
Yeah,
all the biases for a single layer
yeah.
should be IID. It's not a statement about all the parameters throughout the loop.
It is a statement about all the parameters through the neural network, but you were right. So if you're talking about all the parameters through the neural network, then the statistical correlation is the criteria which breaks the free nature, which introduces perturbations, and which introduces interactions. But yes, indeed, actually it happens layer by layer, because NNFT correspondence actually can and work once you have got a single hidden layer architecture. So yes, indeed, for each layer, the weights and biases have to be IID distributed from the other layers. But if you're looking at the overall parameter distributions, then the overall parameter distribution, as long as they are statistically uncorrelated from each other, then you get this central limit theorem working.
So that I can just repeat so that.
Yeah.
So I have three parameters here.
Mm-hmm.
There are a set of W0 weights,
Mm-hmm.
one weight and B0 weights.
Mm-hmm.
So is it true that only when all of them have the same distribution and they're independent from each other, then I take the larger limit, I get a free theory? Or does the fact that just W0 has the same distribution, W1, all the W1 weights have the same
The second one.
distribution? Second one is,
Yeah.
second one is a weaker one.
No, it's a weaker condition, yeah, but it works. So I can actually show you going back why. Mm-hmm. Here. So basically what you are looking at here is the outputs of all the nodes of a single hidden layer. There can be many hidden layers before that one, but you are kind of agnostic to how many hidden layers are before that. What you focus on is whether this guy is statistically uncorrelated across I, right? And whatever is the requirement for that. If you have any kind of, correlations or similarity between parameters that appeared before this hidden layer that breaks the statistical statistical independence of these guys, then that is ruled out.
So in the case that you were showing now,
Hmm.
the other case,
Mm-hmm.
are you seeing in the large n limit
Mhm.
that we have a free theory?
Yeah, that's right. This guy is going to vanish. There is 1 over n scaling. And then higher orders,
So what happens if I have infinite number of derivatives?
yeah.
What happens in the large n limit?
So it still has infinite number of derivatives because this has no dependence on 1 over n.
So your definition of free is just
Right.
You are agnostic about the number of derivatives.
Yeah. That's a very good question, yeah.
It's not free in the sense that
Mhm. Anyway, so let me go to the next detail.
but see this theory, if
Mhm.
you compute the 4.4 later,
Mhm.
it will no longer just be a product of 2.4. Because all you have all these high derivatives in that. No, it will be. It's the product of
Yeah.
the propagator will complicate.
Exactly. Yeah. That's right. That's right. Yeah. Because as long as you can, represent the free action or the quadratic kinetic term as one single term, such that you have quadratic order in the neural network output, that's considered as a free theory here. So long as that happens, all the higher order correlation functions can be obtained by Week's theorem. Yes, exactly. Yeah. So going back here, so let me just mention something that Anindita has already asked me, and it is about global symmetries. So far we have not probed into gauge symmetries. That's an open question on how to introduce gauge redundancies in neural network architectures, because as we know, gauge redundancies are not something that we can see in observables, and these neural network output distributions are all about observables. They give us the correlation functions and other stuff. But what we can actually do here, nonetheless, is embed the global symmetries of the action. Now, I would like to point out that for a generic architecture, you don't actually know the full action unless it is infinitely wide. If it is infinitely wide and IID distributed, then you have the action is pretty simple. It's a Gaussian action. You have the full symmetry. Otherwise, at best, you can obtain an effective action by computing the relevant order interaction terms. So the full global symmetry even cannot be read off from that. And to counter that problem, we introduced this theorem called symmetry via duality. What this shows is that if you can constrain the symmetries of the parameter distributions in the very first and last layer of the neural network, those respectively translate as the spatial symmetries and the internal symmetries of the dual field theory, respectively. And here is just a quick example for that one. So if you choose the last layer parameters, and to give an example, I previously had this demonstration that W1 sigma W1 cosine of W0 x plus B0. So W1 is the last layer last layer parameter. And if you have that as rotationally invariant, then the field is always going to be invariant under this rotational symmetry. Similarly, if the W0 and B0 layers, if they are SOD invariant, then the theory has the spatial rotational invariance. And if the parameters in the input layer have translation invariance, then we ensure that the theory itself has spatial translation invariance. So at least we guarantee the Euclidean invariance through this. The reason being, this is a duality from neural networks to statistical field theories. And if you could actually obtain a neural network that gives you the action of a statistical field theory, that is your favorite quantum field theory on Euclidean space, what you can do is at least ensure that all the correlation functions of the, at least if you could ensure in principle all the correlation functions, if you could check that, if all of these satisfy Osterwalder-Schrader axioms, including reflection positivity, then permutation symmetry, Euclidean invariance, then anything that you compute with the neural network actually can be not weak rotation, analytically continued back to the Lorentzian signature, and then you will get the results corresponding to the quantum field theory. Now, the reverse direction, which is actually very important, that I talked about having effective field theories corresponding to each network. But what about the reverse? Can you take an action that you like, and can you design an architecture which at initialization has the same dual action for its output ensembles? That's a more interesting question to ask for field theory. The short answer is yes, but as long as the kinetic part of the target action is not extremely hard, and as long as the target action is perturbatively non-Gaussian. Under those premises, we can use this particular method we developed here. What we do here is that we break it into a two-step problem. First, we go to this kinetic part, and then we figure out a neural network which will give us an action exactly dual to this kinetic part. And to do that, we have to actually go back to infinite width limit, because it's a Gaussian functional distribution at the end of the day. In general, you can intelligently guess some architecture details like the activation functions, the non-polynomial functions that are defined on each node of the hidden layer. Those are called activation functions. So those can be guessed. And the parameter distributions, they have to be IID, but you can in general also guess what they should be. And then that will give you a neural network dual to this quadratic part. And then there is a next step to get the full action. So what happens here now is that you deform the parameter distribution of the network to update it to something looking like this. Now, if you deform the parameter distribution, the phase-based path integral of the whole architecture actually gets deformed. And the path integral across this architecture in terms of parameters is the same as the path integral in terms of the field theory, which is parameter agnostic. At least explicit parameter dependence does not show up. So now you are actually creating this original neural network through these steps. You generate its outputs, and then you create some operator in terms of those outputs. I'll demonstrate an example in the next slide. Then you create this particular exponent. And for real life, you will probably replace this with a summation for a set of data points. What you do here is that you induce a statistical correlation amongst all the parameters of the architecture. And as a result, this term now gets introduced in the partition function of the architecture. And through that route, it actually shows up in the partition function of the field theory. So in the action, we get this extra additive term showing up. Mm-hmm.
Can you tell me, so let's say I want to add an interaction with let's say lambda 5.
Mm-hmm.
How exactly do you go about changing the parameter distribution?
Mm-hmm.
Is there, like, numerically, what do you actually do?
Yeah. So, yeah. So that question is answered in this slide. So here is the lambda 5.4. And what we will do is we will actually generate a neural network which is dual to exactly this. So it will not be a network having an effective action like this, but rather exactly this. Now, one key point here is that this lambda here for us would be a hyperparameter that will actually, we will decide what the value is going to be. We will have to throw it in. So that's the difference between usual field theory and neural network field theory at this level of development that we have had so far. For this particular part, we actually came up, not me, my PhD advisor Jim did this part in a different work. So there he had defined this architecture which gives you the free action. It's another cosine activation function, and you have got these probability densities. And if you compute the 2-point function of this and then replace B with P, then you have a 2-point function exactly looking like the 2-point function of the free scalar field theory on Euclidean. What that means is that in this architecture, this parameter B has an interpretation of the momentum of the dual field theory. Now you can see here that the parameter B, which plays the role of the momentum, it's defined on a uniform distribution on a ball with a large, the UV cutoff lambda. Now this UV cutoff is something that we choose, users choose by hand. So a priori, if you want to find out what is this UV cutoff and how is this related to the UV cutoff of actual traditional field theory setup, there is not actually any correlation here and there. It is more of a mathematical construction at this point, and you have to embed the interpretation of what lambda is. Yeah. Sorry, can you please be louder? Sorry, can you please be loud? Oh, okay, that's a very good question. So the answer is actually simple, but it is a hard problem. And because it is a hard problem, people use machine learning. They use learning algorithms rather than NNFT. So what you do is, for a given action, for a given free action, this is the inverse two-point function, and you are aware of that. Now, if you go into the papers which are related to NNFT and also theory of deep learning, which are closely related to this program, there are, for a generic activation function, replace this with a symbolic point, rho. You will see that the two-point function has a particular structure, and that shows how the two-point function actually depends on the choices of rho, symbolically. And that gives you an intuition what could happen if you replace rho with logarithm or tangent or something else. This architecture is same for the free field, and then I'll, sorry? The difference is the answer to this guy's question. I'll define a different architecture based on the first one that gives you this action.
Is there a proof that this is the one-to-one mapping? Would I have a different architecture also give it?
Very good question, and the proof is that it is not one-to-one mapping, and the paper by Jim Halverson which showed this actually showed that there can be more than one activation functions that gives you the same free action. And it also goes for the interacting field theories. You can have more than one architectures which gives you the same effective field theory up to some particular order of relevance. So the idea here is that, at least for the sake of computations you want to do, come up with the easiest architecture that you can think of to alter target action. Mm-hmm.
So here, I don't understand what the architecture is. Square root bi square plus n square.
This is a, yeah, this is if you are familiar with these normalizations that happen in neural network hidden layers.
So it's not a weight or a bias.
It is not necessarily just a weight or bias. B is playing the role of the weight.
Yeah. So what is it?
It's a normalization. So if you look into neural networks, different, oftentimes there are different kinds of complicated normalization of the post-activations. So this part is the post-activation, cosine of this. And after that there is a normalization layer with using the weights of them.
So here you have one hidden layer.
Yeah.
There's a B1 for each new one that is.
Right. Sorry? From the previous example that I was showing? Yeah, that was also by same architecture you mean a single hidden layer. Yeah. Now, we actually want to have also the interaction term. So we want an architecture which is not this, but rather dual to this. So what we do is we take this particular architecture, then deform the parameter distribution, the question that you had asked. This is how we do it. So we know the probability densities over A, B, and C, and then we have already defined functional forms of phi. Then we can actually compute this one. Well, numerically you can compute it as a closed form expression. This is going to be pretty hard because it's a product of 4 cosines. Now this is, phi is written in terms of A, B, and C, and you know these normalizations. You have this exponent with lambda, and lambda is a, for now it's a neural network hyperparameter that you have thrown in. In the field theory interpretation, it's the quasi-coupling. So you have got this extra exponent here. And because phi depends on A, B, and C, and this is going to correlate the distributions of A, B, and C, it's going to break the statistical independence. And from central limit theorem perspective, that is going to break the free nature of the field, as in you will no longer have a Gaussian functional distribution. You're going to have non-Gaussian terms, and the non-Gaussian term is this. Why? Because the architecture has its own partition function in terms of these attributes like A, B, and C. And there you have substituted this whole probability density with this new probability density. So then that is equivalent to having these original probability densities times this extra exponent factor, and then there's the J phi term as usual. Then what happens is that the original, this probability density is having here, along with this j phi would have given you this action itself. And now, by having this other probability density, you add this, well, with paying proper attention to the minus sign, you add this particular quadricoupling term to the original action that you had. That's a very good question, and the answer is actually going to be surprising, because I would say if you have to have resemble with actual field theory, the lambda should be much smaller than this radius of the ball, capital lambda.
The reason I ask is because the phi that you're putting there, okay, in the field theory language, the phi that you're putting there is the field.
Right.
And we know when you have interactions, the solution, the phi that we need to, that goes in the Lagrange is not.
Mm-hmm. Mm-hmm.
So it's only in the small lambda limit that you can actually basically use the free field architecture.
Right. And I'll give you a separate intuition as to why lambda still has to be small. Why is that? Because you want this particular probability density to have some statistical correlation. Imagine a large lambda. This is going to vanish. For lambda sufficiently large, even if this is sufficiently small, this whole exponent can just vanish. Then you are not going to have the statistical correlation that's necessary. Yeah, exactly. Non-perturbatively large. Like it can be 10.
Can be 1.
Yeah. It has to be, I would say it has to be small enough. At least, as if you do numerical computations.
You're using the free field solution.
Right.
Like if you were doing field theory, could you have plugged in the free field mode expansion of phi in lambda phi? Ideally, no, unless you're in perturbation theory.
Right.
You can say that it leads to corrections that order lambda square.
That's right.
And I don't care about it.
Yeah.
In that sense,
Yeah.
I'm not doing lambda.
Right. And even if you don't want to go to the field theory intuition, these are cosines. So this lambda phi 4 is actually bound between values of 0 and 1. So no matter what data set you have, this has to be bound between 0 and 1. So then this has to be sufficiently small enough so that this is at least a number of fraction that has some contribution to break the statistical independence of A, B, and C.
I'm sure about that because
Yeah. Mm-hmm.
cost is bounded, but then AI is not bounded because the field
No.
itself can be independent.
No, AI is bounded. It's a Gaussian distribution. So essentially, actually, yeah. Yeah. So let me just point out that actually if you have phi 4 with these, these AI, I's have indices, right? And if you are looking at products of 4 AI, AJ, AK, and AL, then essentially because it's a mean-free Gaussian distribution, you will only have either AI to the power 4th or AI squared terms that are non-vanishing, and those actually AI square, here it would be just, this sigma square, which people generally choose to be 1 or order 1 numbers, and the quartic moment of AI is going to be 3, scales as 3 times covariance.
The field itself
Yeah.
can take arbitrary large.
Well, yeah, that is right.
If I want phi x to be 100,
Exactly.
parameters are very distributed.
That's right. Yeah, it can be arbitrarily large or arbitrarily small. All right, and the last comment is that the parameter distributions that we chose here were chosen to be Euclidean invariants, so that this action that we got here has Euclidean invariance embedded. That means that this architecture that we got by this parametric deformation will automatically satisfy OS axioms through its correlation functions. And then if we actually compute something using this architecture, we can analytically continue those results to the Lorentzian space. So Lorentzian space time. So that is, the reflection positivity in this case can be seen as obvious because these are all local operators. But in general, if you are talking about sorry, I meant to say cluster decomposition is obvious, sorry, I just misspoke. Right, so, right, yeah, so the yeah, that was my bad. The reflection positivity is actually obvious. The proof was given in Jim's paper. Did I quote that paper? Sorry, prepared the slides in a hurry because of the short space between. Yeah. So it is called building quantum fields out of neural networks or neurons, building quantum fields out of neurons. Yeah, so there he proves why for this particular architecture, the reflection positivity is obvious, and we use that to check that even after using this deformation, the reflection positivity can still be seen. The top of my head, I don't remember that particular derivation. So this was the first subtopic, and I will take questions at this point before going on to the next, or if you want, I can go ahead to the next part. Also, there is not, I cannot see a clock, so I don't have a track of time.
So if you have reflection positivity, if you have reflection positivity and you're saying I can analytically continue because of that theory. In the Lorentzian theory, you have a permutation symmetry and you end up with a unitary.
Yeah.
And it's known that in a unitary QFT, parameters like lambda can't be arbitrarily.
Yeah.
Can't be arbitrarily picked. So is there a way to see those things? Because now we know it's equivalent to that. Can you actually put in unallowed values of lambda and see what goes on?
That's a very good question, and what you have asked could be just a next development in this regard, because what we have not yet done in, well, maybe Jim is doing it, others, I was not part of this, is basically look into that and make sure that lambda is not arbitrarily large. What that means is you are taking physics principles and you want to constrain the architecture even more. You want to constrain this hyperparameter lambda. For sure, for unitary theories, that should be done. But this is where you are putting principles, you are taking physics principles and constraining the architecture by hand. It is totally a sensible thing to do. And machine learning community would just say, why do you need it? The point would be, if you don't need it, then if I just simulate anything with, a theory with arbitrarily large lambda, then I know as a physicist it's not guaranteed to give me results that will correspond to a unitary theory, right? So this is where we bring in the physics technology, our physics expertise and further constrain the neural networks. So any more questions, or should I just go to the next subtopic?
I think this will probably open the concept. What guarantee that you had a scalar field?
Oh yeah, very good question. So we guaranteed you have a scalar field because we made sure that this architecture only gives you real valued answers that are that have dimension 1. And we made sure of that by having these weights and biases which are themselves real valued. For example, right now we are developing this minimal SUSY and we had fermionic developments. We actually had to choose weights and biases carefully as Grassmann valued numbers or combinations of reals and Grassmanns to make sure that these outputs are satisfying certain anti-commutation relations. Versus here, these guys commute with each other. That is made sure. So this is why we can guarantee these are scalars. Also, we made sure they don't have any structures like tensor outputs or anything. So, yeah.
You're saying that you're not able to gauge boson because you don't know how to incorporate gauge structures.
Yeah. Well, at least I don't know if there's any other group working in this direction at the moment, or if Jim is talking with any other group people in this regard. So there are quite a few people right now working on these. Koji Hashimoto, then Jim, and a few other people here and there working on neural network and quantum field theories. No, we are building on the fermion to have the minimal SUSY. So yeah, we will finish the minimal SUSY in a few months and then put it out. Good. So then you have to go back to traditional machine learning for field theories. Because people use these beautiful normalizing flow diffusion models to simulate field theories on lattice. Those work for scalar field theories. If you use those to simulate fermionic field theories, you are doing this on Lorentzian space. So you are going to pick up an extra phase, which gives you a sign problem because you have got this e to the power I s and on lattice that picks up an extra minus sign. So essentially you are going to get a probability density of these neural network outputs that blows up. So it is a mathematical contradiction, which means the neural networks, their machine learning models, they fail. They don't give what it should. Now this is useful because we are doing everything on the Euclidean space, and yes, I know that fermions on Euclidean space is not very well defined, but if you go back to 1970s, 1980s, there actually was a lot of work on fermions and SUSY on Euclidean space. So then we realized that actually you can hopefully do the fermionic field theory on lattice but on Euclidean space, and then you have to just analytically continue those results back to the Lorentzian signature. And more importantly, I recently talked with Joydeep Chakraborty in IIT Kanpur, who pointed out that in fact you don't always have to do these OS axioms and then analytic continuation. Apparently there is this, he has this hit kernel method that lets you continue the results more easily to Lorentzian signature. Mm-hmm. Yeah, I have not yet explored the connection between this and that, but he pointed out that indeed the results of NNFT can be more easily connected to actual quantum field theory. By that I mean by actual quantum field theorem and corresponding field theory on Lorentzian space. So if there are no further questions, I think I have maybe 15 more minutes. Let me give you an overview of how you can, in your spare time, if you're interested in theory of deep learning, there are lots of open-ended problems out there that empirically has been seen but has not been well understood, and people are not bothering to think very deeply about those and develop theories. And in fact, amongst the frameworks that we have got, there are amazing works done by Dan Roberts and Sho Yaida as a whole on theory of deep learning. Then there's Ivo Silverstein, who brought in this energy conservation method for learning algorithms. Then there's Alex Maloney and Jared Kaplan, who brought in random matrix theory for neural scaling laws. And then we did this one where we brought in Wilsonian RG for understanding the learning quality during after supervised learning happens, and how the network predictivity changes as it coarse-grained out data details. So this is a very interesting work with one particle physicist, Jessica Rowe, who is a string theorist, and Zohar, who is a condensed matter physicist. So here is some motivation on why a priori you are throwing Wilsonian RG into this domain of machine learning performance. If you have been paying attention to this all AI and machine learning buzz, you will notice that people in ML community, they throw in words like RG coarse-grained. They'd be like, oh, machine learning is RG, ad hoc, hand-wavingly, without any notion of what RG even means. So that's actually garbage, because you need to have a scale, you need to have a method to coarse-grain out degrees of freedom. You have to define how you are going to, which degrees of freedom you are going to coarse-grain over. People don't define those, they just throw in the word RG. But if you think about this problem a bit more closely, there is this whole problem of how the outputs sensitively depend on the data. It is not well understood why machine learning works, as in, if you change data from one data set to another data set, take ChatGPT, large language models, take those architectures, and instead of using them for language processing, you use them for some kind of mathematical semantic question and answer generations. Those models still work. Those models have been able to prove some theorems and has been useful at least for high school level physics and high school level mathematics and basic undergraduate level mathematics. You can look into these works by Princeton group. And that's very interesting. So what that means is that somehow these models have a capability to understand intricate natures of data and somehow forms a universality class across data. And what is data? It is information. So understanding how the data and the relevance of different data attributes show up in the output is going to tell us what is the underlying information theoretic properties of these models. So in order to actually look more closely into that, we wanted to know how the precision of the outputs depend on the data attributes. Why? Because at the end of the day, this is an important question if you think about machine learning for particle phenomenology or experimental particle physics. So there is a lot of problem there, right? We are trying to pick up signatures of beyond standard model particles or new physics, but we don't know whether those are real signals or whether those are noise or a combination of both. So there is the pressing need for scientifically rigorous models that can distinguish between noise and actual data or signals, and we should not have to wait for 10 more years or 15 more years to get there. We should be able to look into the machine learning models, AI models we have today, and do some clever analysis on those models and actually go ahead to analyze those mixtures of noise and signals. So to get to that state, then there would be some necessary points, and these necessary points are that for a particular machine learning model, you should be able to look into the data, and even before you are considering the output and the precision of the output, you should be able to tell that these are the classes of relevance of the data features or attributes. And then you should be able to figure out how the output itself depends on these various classes of features or attributes. And then, once you figure out this correlation between the output and the data relevance, then you should be able to tell that if the data is now suddenly missing, some part has been coarse-grained, then what is going to happen to the output? How is the output going to evolve? Now, from the field theory perspective, it actually has the same steps as RG. Why? Because outputs have their own statistical ensemble, have their own statistical distribution, which is mathematically dual to these statistical field theories. Now, if you are coarse-graining out some attributes of the data, then essentially the actions dual to these architectures are gonna change. And if the actions are gonna change, that is inducing some kind of an RG flow in this action space. So then the actual prediction, as in the output of the neural network, should change, because if the action changes, then the one-point function of the field should also change. So here is now some technical details. I'll keep it brief. But the idea is, even if you have very large neural networks, no matter how much nicely you train them, they are always gonna generate noisy outputs. And to demonstrate this, symbolically, this is the output F instead of phi. This is the target, some very nicely created data from some quantum computer, some quantum device, Rydberg atom arrays that you have generated. But even in this case, very nice training over parameterized neural networks known for their performance, there would always be some difference between these two. Note that this is the output on the test data. So you have perfectly trained network, you have just generated the output for the test data set. The role of being over-parameterized means that, so over-parameterized neural networks are known to have extremely good learning performance. So they can learn any functions out there, any distributions out there, in principle, if you sufficiently train them for a long time. So we actually retain in this particular limit of over-parameterized neural network first, because the actual analysis is mathematically analytically tractable there. If we move from this limit, then there are just going to be extra terms in these actions dual to these over-parameterized neural networks. So we are gonna look at the RG flow of the action if we remove data features. And to yeah, it just helps us to understand how the RG flow of the action happens and how the one-point function evolves. Now, even for the output on the test data set, there is always going to be difference from the target, and we generally note that by some white noise. This white noise has a covariance which is called reach, and in machine learning community, the predictive power depends on this reach. In fact, depending on the value of this quantity called reach, sometimes you will see this thing called gradient descent that happens. There is a double descent that happens. Sometimes the learning performance can be very good, or it can be very bad, or it can go through a peak, then become good, then bad, and good again. Things like this happen. So this itself is interesting to machine learning community. But what they don't have a notion of is how actually this reach depends on the data features or data attributes. That's where the RG came in. Because we actually wanted to test if data features are getting removed systematically, how will the reach evolve, how will the noise evolve, how will the one-point function of the network evolve. And this is what we do. So this is going to be a Wilsonian RG framework that can track the evolution of the noise. So this is going to be useful because in principle using this, one can go from bottom up, from a noise dominated learning regime where the data has a lot of noise and the network performance is bad, but from there you should be able to go bottom up and find a regime where the predictions become precise and trustable. Now, to focus on the RG of the action, I would just like to point out that now we are not exactly going with the quantum field theory actions or QFT on Euclidean fields, Euclidean background. What instead we do is actually create this replica partition function, which is actually m copies of the same phase space of the neural network. And this action itself, it has the original, let me just go here, it has the original quadratic term. This is the inverse kernel, and f are what we called fields before. These are still fields, but there are m copies of that. So this is the free action over m copies. But now there is an additional term here given by this factor called eta. Eta is the number of data points. And if this was an infinite number of data points, you can see that this is in the action itself. So if there was an infinite number of data points, the contribution of this part will just be trivial. But for finite number of data points, these different phase spaces become correlated with each other because of data disorder. And this is where the data correlation shows up. Here is this exponential term, and here is this quadratic factor that governs the distance between output and target. This is known as MSE loss or quadratic loss or L2 loss. It could be something different. Machine learning community has many loss functions. You could substitute this with other loss functions. It is a simple thing to have a quadratic term here, so we did our analysis with the quadratic term. But the point here is that you actually can show how the data attributes interact with each other, whether they are highly relevant for the inference problem or whether they are less relevant or between these high and low relevant classes. And this can be seen by a method called spectral decomposition. So for
Can I think of it as an n particle?
Yeah, exactly.
Eta is some Lagrange multiplier.
Exactly that, yeah, it is exactly that. And this Lagrange multiplier's contribution is just going to vanish if there was a large number of data points. But for finite data points, it is not going to vanish. So if yeah. So it will mean that you have a lot of constraints, but e to the power minus a large number, the partition function itself is, yeah. Right. It will be a digression, but I have a nice related work slide. But let's just continue with the science in interest of time. So essentially here you can see how the different classes of data features interact with each other and how coarse-graining one class is going to affect the one-point function that we retrieve from this action. And in order to go into the details, we actually choose a basis that is known as the kernel. It is called the kernel Hilbert eigenspace. So it is like a universal eigenspace for all possible neural network kernels or two-point functions. The NNGP is referring to a Gaussian process of the neural networks, which is the over-parameterized limit when you only have this quadratic term. So for this particular case, NNGP, we carry out this kernel Hilbert eigen decomposition. And then those modes, those eigenmodes are given by phi. In terms of phi, we decompose the output and the targets, and these are just amplitudes. And then we find out a particular threshold in the space, in this kernel Hilbert eigen space. We find out a particular threshold for which we can coarse-grain out some of these phi modes. So in order to find out what is this threshold, you actually have to closely inspect the problem at hand, the target data and the test and trained data sets that you have got. So that actually can tell you what is a threshold. This is the threshold, sigma square over eta. Sigma square is the reach or the noise covariance, and eta is the number of data points. And at this threshold, there would be a sufficient number of these eigenmodes that decouple from the overall inference problem. As in the output, the one-point function of f does not get affected much from the modes that fall below this particular threshold. So this is actually known in the machine learning community. So this much was known. There are some modes, and the one-point function doesn't care about these modes, because in the limit, when these are both large but the ratio is very small, those modes, eigenmodes, decouple. Fine. So we know that much. Then what we wanted to do was actually see if we could just coarse-grain out these modes lesser than this threshold layer by layer, like in momentum shells. What will happen? Now, the modes with low eigenvalues have the interpretation of high momentum modes because they are more and more irrelevant. So you carry out this momentum shell coarse-graining, and then what you notice is that in this replica partition function, the action suddenly will get, by suddenly I mean after a number of steps, it will get contribution from these prefactors Fm for the modes that fall below this threshold that I specified earlier. Now why is this interesting? Because this is no longer the same action as this part. What this means is that if you have two networks, the first network somehow has, imagine two different networks. Both the networks have this NNGP limit, but the architecture details are different such that the first one can only have these eigenmodes versus the second one can have both these and these eigenmodes, like k less than the threshold, k greater than the threshold. And then in one case you are only going to get a prediction, a one-point function of the output coming from this particular action, and in the other case you are going to get a prediction or a one-point function of the output that comes from this effective action. Yeah, f of m is defined here. It is the prefactor. It is not exactly the eigenvalue, but rather it is a coefficient associated with each of the eigenmodes. If you take the output and put this in this Cornell-Hilbert eigenbasis, then all these dependence of the weights and biases and other architecture details shows up here through these. So the data explicitly influences how these Cornell-Hilbert eigenmodes would look like, and the dependence of the architecture shows up through these FMK modes. And Fm lesser means k is less than, k is such that the eigenvalues are less than this threshold. And k greater means the eigenvalues, sorry, it's the opposite, my bad. Yeah, but k could also go from minus infinity to infinity. We just kept it simple. Exactly, yeah.
So I thought you have one lambda for every parameter.
Lambda for every parameter. So which lambda?
What happened to the parameterization?
So the parameterization shows up in these coefficients. So the output explicitly depends on parameters for sure. But the moment you are going to this neural network Cornell-Hilbert eigenspace and you're decomposing the output into those eigenbases, all the dependence of the parameters gets absorbed into these coefficients, these amplitude factors. Yeah, it is non-trivial, so anyway, just to recap, so for k, which is the modes, these eigenmodes, when k is such that the eigenvalues lambda k is less than this threshold, those eigenmodes decouple, and for k such that this lambda k is greater than this threshold, those are relevant eigenmodes.
What is phi k really? I only have one neural network.
Yeah.
I have one function that you make k copies of it.
No, you don't make, you make m copies of it. But this m is not related to this k. For any neural network, you can always take its two-point function. And the two-point function does not even have to have this replica action structure. You could also go back to this previous statistical field theory description that we gave. So anytime you have got a neural network, it has a two-point function of the outputs. It's the covariance matrix of the outputs. And that...
Here the neural network, are you calling f of mx the neural network?
I'm calling the output of the neural network as f of mx. So phi earlier had the field interpretation, so f was phi before. Yeah. Okay. All right. So let me just show you what we get from this, all these tricks. So what we show here is that if you have a data set, irrespective of the models, so irrespective of the architecture details, parameter distributions, if you have data set such that this kernel Hilbert eigenspace have modes that are all Gaussian, so modes have their own distributions and that depends on the data distributions. Now if you have Gaussian modes, then this coarse grading gives us some trivial result. This result was actually known in a different format. All we did was give it some RG interpretation. So each momentum shell RG is going to just give an incremental value to this noise covariance just by an additive term over the coarse-grained eigenvalues. But, so this is, well, nothing new for the machine learning community from theoretical physics, but it doesn't stop there. It actually gets interesting after that. And this is where we actually give something new to the machine learning. Oh, all of them being Gaussian, so it is an interesting question. I guess the physical interpretation can be that the data is such that the frequency of the data, it could be resolution, it could be temporal frequency, it can be some kind of a noise-based, sound-based frequency, sonic frequency. Those are going to be Gaussian. So for every kind of data, sorry? No, there is no field theory. It's a purely statistical interpretation here. So whenever we are talking about the data distribution as well as this eigenbases, in most of the works, I have never really seen a field theoretic interpretation anywhere over those distributions.
There's no field theory interpretation in what sense?
So it's not a functional distribution. It's just a distribution of random variables. Yeah, because what happens is that for real life data, this phi k's becomes vectors. They're not functions of inputs. They depend on the inputs. So the reason we write them in this way is because they explicitly depend on the inputs, but not in the way that you can give it a functional distribution interpretation.
So are you defining hierarchy and not?
Yeah. Right.
And you are not from that. You are not integrated out in.
We did already. So we defined the high and low energy modes with this threshold.
So what was the intuition for saying, okay, these are high energy modes, and whatever I want to learn doesn't depend on these high energy modes?
That's a very good question. So for that, you actually have to look into these, the actual lambda values that you are getting. So there is a plethora of literature out in the machine learning community which has established that as long as these eigenvalues associated with these eigenmodes fall below this certain threshold, and this threshold you can know it in terms of data points and noise covariance, initial noise covariance. So as long as it falls below that, you have to take the intuition from the research done by machine learning community that these modes are equivalent to high energy modes because they don't contribute relatively enough to the outputs. So by initial noise covariance, I mean you start from somewhere, right?
Is it a trained model?
It is a trained model. So initial is not initialization. So initial here means you take the trained model and you take the full test data, or potentially think of you have the whole universe as a full test data, and then whatever you get as the output, that's the initial output. So if there are no more questions, let me just show these interesting results and finish up. So now if you have data distributions such that these eigenmodes themselves are no longer fully Gaussian, rather those high energy modes become perturbatively non-Gaussian. Well, they can also be non-perturbatively non-Gaussian, except we don't know how to do that analysis, so we restrict it to a case where we could do some closed form expressions, get some closed form expressions for the RG flow of the noise. So essentially there is a lot of non-perturbative domains associated with these kind of machine learning output performance that we could not even probe into because we still lack the technologies. By technology, I mean theoretical methods. So imagine you have got this scenario where below a certain threshold, the low energy modes are still Gaussian, also for the sake of computational simplicity, while the high energy modes are perturbatively non-Gaussian. In that case, you can do this momentum shell RG, and you can show that, in fact, now you have got an effective action which has obtained a spatial RG flow of these noise covariance. Now, this term itself, it was, the MSE loss to start with. So the MSE loss had this denominator. Now it is still the MSE loss, except the denominator has evolved with the spatial RG. And what does this tell us actually? To do that, to see that, we actually had to test this on some kind of a real life data set. So we wanted to be as much model agnostic as possible, because at the end of the day, this is supposed to be a general framework. So what we actually chose was that we decided that let's just look at a case where the kernel or the two-point function of the neural network architecture can be decomposed into first and second order Hermite polynomials. So this lambda 1 and lambda 2 are pretty generic. It could be any model as long as the two-point function here means the covariance matrix can be decomposed into this. Now imagine a target function. We kept it pretty simple and had a target function as a fifth order Hermite which has no overlap with either of these modes. Now imagine two different networks. The first network, which has only got this H1 mode in the kernel. And imagine that network is learning this one and giving you some prediction. That is actually this blue line. And then secondly, what machine learning community did not know before, this is a new result, the orange line, is that if you have the other network which has both the modes and you want to learn this, but then you coarse-grain this one out. So initially you had this, you could learn this, but then you have coarse-grain this one out. So intuitively, would there be a contribution from this mode for the learning procedure? Intuitively, no. Machine learning community and their results said no, if lambda 2 was non-zero. But our results showed, the empirical results were non-zero. The empirical results say that there should be some contribution from the coarse-grained modes. Our results actually could fit for what the empirics were showing, and it showed that although this has no apparent overlap with this target, even if you coarse-grain this out, some effects of lambda 2 are going to actually show up in the prediction. This is the average prediction, average output, that is the one-point function of the neural network output. So this is a place where we could actually provide a theoretical understanding of non-trivial output that machine learning community obtained before. And then secondly, there is something known as neural scaling laws. We could also provide theoretical explanations for this. So what this is actually you take a trained network. You have trained them on these cipher and MNIST data sets. These are the data sets of pictures, images of handwritten digits, or images of cats and dogs and various other objects. So you train on them, and then you test on a classification task of two images, 8 versus 9, and another task of classification between 0 versus 1, images of 0 versus 1. Then what we did was that we decided that we will keep increasing the number of data points in our test set, but then we will also introduce something called learnability threshold, which is essentially a fraction of the eigenmodes that we are going to coarse-grain. For a chosen value of this fraction, then we are actually going to use our theory, which is essentially going to give us, so this is the part, the MSE loss for the coarse-graining for this learnability threshold should take this particular form. Then the point here is that you keep increasing eta and you choose these learnability thresholds, the fractions of coarse-grained modes. Now what does your theory tell the test loss has to be? So the theory actually gave test loss curves, these solid lines, which are pretty close to the empiric ones, which are the dotted, the dots. But if you look into the machine learning theory predictions, they had curves that went like here. So they went, those curves could not explain what the empirics would show in this particular case. So these were two demonstrations that our Wilsonian RG, although it's very simple, it is just using this neural network Gaussian process, over-parameterized neural network limit. We have not even considered what happens when you have finite neural networks, as in non-Gaussianities. The only non-Gaussian it is because of the Lagrange multiplier with the eta term. But even in that scenario, even keeping these modes as simple as possible, keeping them perturbatively non-Gaussian, etc., we could actually come up with non-trivial results for the machine learning side. and explain some of the empirical results they already have obtained. Now, let me just wrap up. So there are future directions. For NNFT, we are working on the SUSY, and there are also works to be done for the highest symmetries. And then the more important part that we actually want to probe into, for those of you who look into field theories, with the simulation of gauge theories by machine learning, there's been a lot of ongoing thrust in that direction, use of geometric deep learning, equivariant neural networks for gauge theories on lattice. There is a lot of work also to be done there using the NNFT correspondence, but first we need to actually bring in principles from gauge theory and constrain the neural network architectures to make sure that the architectures know what a gauge invariance is. And secondly, this Wilsonian RG framework provided us good theoretical support for the empirically sane neural scaling laws. And we want to see in future if this can actually predict some analytical form of scaling laws that the machine learning community keeps seeing. So let me just conclude here. So I provided a library that provides it's a library between the space of neural networks and the space of statistical field theories, but that allows you to do computations using these initialized architectures directly on statistical field theories, and in certain cases using these OS axioms or other methods, you can extend that for quantum field theories. And secondly, I produced this other framework we have developed using momentum shell RG, where you can bring in your physics intuition and physics methodologies to develop theoretical results, a theoretical intuition behind the plots and the curves that machine learning community keeps seeing through their own experimental results. And last but not the least, many thanks to all the collaborators whose results I have showcased here. And finally, thank you for having me. I'll take all the questions, including those on the second subsection. Mm-hmm.
Is there a reason using neural networks to do quantum theories? I mean, what can we do there that we could not do in other? I understand the part where using field theory to understand machine learning, neural networks can understand predictability, how they're done. That seems very useful.
Right.
But what is the other way of doing?
Good question. So the other way is important, because if you look into it, NNFT correspondence gives you an alternative way away from MCMC to sample fields. If you could theoretically know architectures that correspond to a Fermionic field theory with the interaction term that you want, you don't have to do MCMC to sample a field configuration. If you look into all the computations people do in this nuclear and some parts of particle phenomenology, they often have to do a lot of many steps of MCMC, and not just MCMC, there are other convergence methods as well to make sure the probability distribution of your network matches some target probability distribution, so that you can just sample one field configuration that's good enough for other computations. So this NNFT correspondence provides an architecture where the output itself is a sample from the target field distribution, and then you can do computations with that sample output.
There was recently this work which had Bayesian RG. And then somehow there was a length scale associated to all parameters.
Right.
That helped you separate out UV parameters.
Right. So I did not discuss that one in here, because that's
similar to, I don't know if it's clear, but that somehow seems cleaner. In the sense that
in what sense?
I can, I know the field theory interpretation.
Right. So
your field, you can expand it. You have these parameters. If you integrate out some parameters from this neural network, you have an IR neural network.
So I should mention, Bayesian RG is about information theoretic RG. So information theoretic RG is not always momentum shell RG. And the cutoff that you are talking about, that is in the space of Fisher information metric, right? So if you look into that one, there is indeed coarse graining over the neural network parameters. And because you are coarse-graining over the parameters, parameter distributions evolve. In turn, the dual actions evolve. So the actions evolve, but the evolution of actions. Now, when do parameter distributions evolve in real time? During training steps, right? So the deal there is that training is inverse of this coarse-graining over the parameters. So in the sense, during training, the action actually upgrades. And what we do here is that we find out a very systematic, in Bayesian RG, we found out a very systematic way to coarse-grain the neural network parameters as if you're flowing in the opposite direction from target to initialization. That actually corresponds to Bayesian RG. And the reason that is important is because if you want to simulate some field theories which have maybe critical points, or maybe they have non-locality where usual RG methods might fail. But the reason that is playing a different role is because that does not have any immediate application to the machine learning world. That is just a way of understanding the evolution of this field theory action during training. Also, that is not always guaranteed to be monotonic. So I could discuss that in more detail, but my point is that should be used carefully. It is not as trivial as it seems. So the Wilsonian RG, as you can see, the Wilsonian RG is actually parameter agnostic. It's focused on the relation between data and RG flow of the action, whereas Bayesian RG is focused on the coarse-graining over the parameters and the RG flow of the action. So these are two different kinds of RG flows.
But I thought the neural network field theory correspondence is when you say action, you mean parameter distributions.
So I was not discussing neural network field theory correspondence. Bayesian RG is an extension of NNFT to Bayesian RG. Rather, Bayesian RG is a different framework that gets connected to NNFT. Wilsonian RG framework is a totally different research direction.
So Wilsonian RG doesn't, I mean, but still parameter distribution evolving.
Where? In the Wilsonian RG? So you're talking about some different problem. You're not talking about machine learning performance. You are talking about the parameter distributions evolving by some method which can be trained.
I'm just saying, when you talk about the field theory, I thought the point was that the field theory action, you can do a path integral, you can compute correlation.
Right.
And on the other side, you have this density function of parameters.
Right.
And you can do an integral there.
Right.
And you can compute correlation. Now, this Wilsonian RG, what is the interpretation in terms of?
In NNFT, what is so you want to know what is the interpretation of the same Wilsonian RG in terms of the probability density of the parameters. So in this scenario, we do not even connect it. Wilsonian RG could be done on the parameters, but we don't want to spoil the performance of the model, because what we are trying to say is what happens if we keep the model's training amount the same. So have I ever gone back to train data set? No, I'm talking about a very perfectly, very nicely trained neural network. So that means, it's pre-trained weights. We don't want to change the weight distribution of the neural network in this setting. Hence, we are not coarse-graining over the parameters. So the problem premise has changed.
So this is more natural in the usual way that we think about it. Here the coarse-graining is over the amount of data you feed.
So I should maybe clarify. If you think about neural networks learning, there is this term called pruning. Pruning is a coarse-graining over parameters. So that is connected to the Bayesian RG question that he is asking. But my point is that is associated with training dynamics, and this is after training dynamics. This is only for the test loss. Test loss has nothing to do with training dynamics, because Bayesian RG has a connection with the training time. There is no notation of training time here. So think of this as two different kinds of RG. You can have an initialized network, some dual action, then you train it. During training, you coarse-grain over the parameters according to inverse of Bayesian RG that causes this RG flow of the NNFT action. Then you reach some target. The target is the UV in the information theoretic sense. Now you have a perfectly trained, apparently a nicely enough trained network. Now you want to test that trained network on some other data set. That's the interpretation of what is a test generalization of a neural network is. And there you decide, well, fine, the training has worked enough, so why don't we now change the degrees of freedom of the test data set? Now what kind of RG is changing the degrees of freedom in data set going to show up in the action? So now this is about actually the trained action. Trained networks dual action, and that undergoes a different RG flow. Yeah. 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 So basically these were two different classification tasks. And for this each of the classification tasks, we actually took the networks. So essentially here was kind of a comparison that we have got one network, like two copies of network. In one network we have decided that the test data set is actually the number of points times this, the learnability threshold, or as if that network does not even know about the existence of these coarse-grained out modes. So essentially the things with error buzz here corresponds to this first network's test loss. So that is agnostic of any coarse-graining, and then there are theory curves. The theory curves as if you have got a sister network that had originally the information of all possible kernel Hilbert eigenmodes, and then you use this learnability threshold to coarse-grain those one out. And the question then is, are these going to differ? So basically you can see there in the solid blue line, it is actually very small value of learnability threshold. So that means you have coarse-grained out very little amount of modes, and in that case, the two networks behave like similarly. But if you coarse-grain out more, like this is 0.3, now there is a deviation between the experiment and the theoretical prediction. What this means is the first one, there's a deviation between empirical and the theoretical prediction. What this means is that this network over here, it is aware of the existence of these other eigenmodes, and its test loss would have been lesser because of the existence of these other coarse-grained modes. Whereas the empirics, which is corresponding to a neural network that did not know about these coarse-grained modes, it has a higher test loss. And in fact, this is what we want actually. So if you have the information available about the coarse-grained data attributes and data features, we expect that the learning performance, which shows up as this test loss, MNC loss, it should be better. That's what we expect.
And how would you use in practice? So you would first try to use the coarse-grained object or coarse-grained network to make the prediction, and then you would gradually
So it is actually a good question. So what we did was only these dots are only the empirical ones, and we used a CNN just to train it over the same amount of relevant or low energy modes. As for the theory, we actually only did the theoretical calculation on pen and paper without using the neural networks architecture details, but only just taking in its replica action. Sorry? Yeah, this is the test set. Sorry? Yeah, so the solid lines are the pen and paper calculation based on the framework that I just introduced. And the dots are the experimental results for which you write the code, where you pass these, 8 versus 9 or 0 versus 1 through the network, and you make sure that the network is a different one than these ones. It is defined in such a way that effectively both of them have the same number of eigenmodes, except the empirical one does not know about the existence of the other eigenmodes. It's just a network based on these selected set of low energy eigenmodes, and the theoretical one is an analysis starting from the space of all eigenmodes, also high eigenmodes, and the theoretical, so the neural network is in theory, but rather what we do is the computation of these actual replica action for this other network where all the both high and low energy modes were present, and then by Wilsonian RG we study how the test laws should have evolved if you coarse-grain out the higher modes.
So practical application would be if you have a very detailed image to classify and
Yeah.
you want to start off with the whole screen
Exactly.
network and then
That's right. That's right. So we did not go super detailed. We went with cipher 10 data. Just yeah.
is that what you're doing here?
Yeah. So this was also a simple classification: sheep versus truck and automobile versus bird. Sorry, which one? Yeah. No, it's a learning threshold. It means a fraction of the kernel Hilbert eigenmodes that you coarse-grain over. So essentially, if this fraction is lesser, that means that the theory would have a smaller coarse-grained effect from the higher modes, and the empirical network which generates the test laws should have a better match with the theory. That's what happens here. Yeah. Yeah, exactly. You are integrating out a lot. No, thank you for. Yeah.
For 1.5 hours, I think we should thank Anindita for a
Well,
very nice talk.
thank you for all the questions.